Okay, welcome back everybody to another video lecture from Mrs. Semino. This time we are still talking about chemical quantities, but this is the second part of that chapter. And so today what we're going to be discussing is how to go from moles, convert that into grams, and then how to go from grams and convert it back into moles. So we're either going to be going from moles to grams, or from grams to moles, or from moles to liters, or from liters to moles. So these are the conversion factors that we're going to look at today. So our more formal definitions for today are to describe how to convert the mass of a substance into the number of moles of a substance and then back from moles to mass. We're also going to identify the volume of a quantity of gas at standard temperature and pressure. And we'll talk more about what this is, but this is basically doing those conversions from moles to liters. So just a little review. I know you can't see this up here at the top, but it says molar mass. Molar mass is a generic term for the mass of 1 mole of any substance. And remember, the units for that is expressed as grams over moles, and maybe even a better way to write that is grams over moles, and that's the molar mass units. A couple of other ways that we might say this is we might call it, instead of the molar mass, we might call it the gram molecular mass if we're talking about molecules. We might say the gram formula mass if we're talking about ionic compounds, or you might even see it the gram atomic mass, and this is just for individual elements. But honestly, in class, I'm always just going to be talking about the molar mass, but you might see in your textbook or in your worksheets, maybe they're asking for something that sounds different, but it's not. You can just see the word molecule here, molecule, formula, remember the formula units for ionic compounds, and then atoms for individual elements. So the molar mass is just a much broader term than these other specific masses, and so that's why I'll be referring mostly just as the molar mass. So here is, it says example, again, sorry you can't see that up top here, but it just basically says calculate the molar mass of the following and tell what type it is. So what type, using the terms we just saw from the last slide. So the first thing that we want to do is we want to see what type of compound it is. We have sodium and we have sulfur here. So we have a metal and a non-metal, so this is going to be an ionic compound, so that's why we're calling it a gram formula mass. And let's just go ahead and review how to calculate the molar mass. So I've got sodium, and there's 2 sodiums here times 23, and then I have sulfur, and I have 1 sulfur times 32, so then 23, oh actually 46, this should be 46, plus 32 gives us 78, and that's the total that we're seeing right there. If we look here at this next compound, we can see that it's dinitrogen tetraoxide, but it's a non-metal plus a non-metal, so that's going to be a molecular compound. So that's why we're calling it a gram molecular mass. And so if we were to do the same activity here, we'd find that the gram molecular mass, also known as the molar mass, is 92 grams per mole. Carbon here is its own individual element, so we might use the term gram atomic mass from the last slide, and of course this one is going to be 12. Now I'm going to do this next one here, this calcium nitrate, with you, just as a review because it's kind of tricky with these like little subscripts that we have here. So first off, we would call it a gram formula mass, just like we did up here, because it's an ionic compound. We have the metal and the non-metal. But let's go ahead and calculate that gram formula mass. So I've got calcium, 1 calcium at 40. I have nitrogen, and now I'm going to have 2 nitrogens because it has this other subscript out here. So that's going to make it 2 times 14. And then oxygen, we have 6 oxygens at 16. And I just go ahead and I do a little math here. So 1 times 40 is 40, 2 times 14 is 28, 6 times 16 is 96. We add this up, and then the gram molecular mass for our calcium nitrate is 164 grams per mole. Now just a quick little review here. This is glucose right here. These should be subscripts again. And so this is going to be, these are all non-metal, so it's a molecular compound. So we would call this a gram molecular mass. Then down here we have our ammonia phosphate. This is an ionic compound, so again we're going to use the term gram formula mass for those. So again, I know these terms can sound tricky, but just remember I'm just generally going to use the term molar mass when we're talking about these. So this is a little review from the first unit, and it says the number of grams in 1 mole of atoms, ions, or molecules. So that's what we're calculating. We're calculating that molar mass. We can use this number to make conversion factors from these. So to change between grams of a compound and moles of a compound, we just simply use one of these conversion factors. So just like you might say there's 12 inches in 1 foot, we can say 1 mole is equal to the molar mass. The only thing that's tricky about this is remember that the molar mass will change depending on what your element or compound is. So our example that we're going to be working on to demonstrate this is, it says how many moles is 5.69 grams of sodium hydroxide. So we'll see the solutions on the next few slides. So again, here's our question. And so the first thing we need to do is we need to change our grams of sodium hydroxide to moles. So recognize that we're going from grams to moles of a substance. And so we want to set up our given. Then we need to put it with a conversion factor. And then it's always helpful for me if I put over here moles of sodium hydroxide of whatever I'm trying to get into over here. It just kind of helps keep me focused. So we need to change this into moles. And so one of the things, in order to find the mole, is we need to know the molar mass. So we have our sodium here at 23 grams, our oxygen at 16 grams, and then 1 mole of hydrogen at 1 gram. So if we total that up, we're going to find that it's 40 grams per mole. And this is our molar mass for sodium hydroxide. So we're going to put our 1 mole for every 40 grams there. Now we have our value here, so we're just going to go ahead and do the math. And so when we do this math, we're taking this value of 5.69 and we're dividing it by 40. And we come up with a value that says 0.142, and I'm hoping that you realize if you did this on your calculator, you should have come up with a value that was 0.014225 or something like that. Notice in our final answer here we only have 3 significant figures because in our given we only had 3 significant figures. On these next few white slides, I'm going to go ahead and do a few more examples, and so I'm going to start off with some gram to mole conversions. If you're totally getting this, go ahead and skip to the volume conversions. Otherwise, stay tuned for some of these example problems. So our first question here, it says how many moles are in 2.10 grams of water. So I always kind of start these problems off by putting a little box around what my final answer is going to be with, and I'm going to be starting, or my given is 2.10 grams of water, and of course the word is water here, but we need to know that the formula is H2O. So I boxed my final thing, and I've just simply underlined my given. That just helps keep me organized when I'm doing these problems. So the way that this is going to look is I'm going to take my given, which is 2.10 grams of H2O. I'm going to set up my little conversion factor, and then I'm going to write moles of water over here because that's what I want my final answer to be in. So I need to go ahead and think of the conversion factor that I want to use. And since I'm starting off in grams, I know grams is going to have to go on the bottom, and I want to get into moles, so moles will go on the top. But now you might be like, okay, that's good, I have the units, but what are the numbers that I'm plugging in here? Remember, if I'm using a gram and mole conversion, I need to find the molar mass. So for water, it's H, and there's 2 hydrogens times 1 though, so that's not too bad. And then oxygen, there's 1 oxygen, and its atomic mass is 16. So it says 18 grams for water. So I'm going to put my 18 here, and that's equal to the mass of 1 mole of water. Okay, so perfectly, I have this set up. My grams are going to cancel out of water. I'm going to be left in moles of water, and that's what I wanted for my final answer. So we just need to go ahead and do some math on this. And I come out with an answer that is 0.11666 for like a really long time. 6 is out there. So what we need to do is we need to look at our number of sig figs, and I have 3 sig figs here. So I'm going to only need 3 sig figs here in my answer. But notice this 4th sig fig here is bigger than 5. So my final answer for this is going to be 0.117 moles of water. And that's my final answer, so I want to go ahead and put a box around it. So the next example problem we're going to do, it's actually really a review from that introduction to moles part 2, going from moles to grams. So our question says how many grams are in 88 moles of carbon dioxide. So again, I want to start off by boxing my grams, underlining what my given is. So I'm going to go ahead and write my given, so 88 moles of carbon dioxide. I need to go ahead and set up my little conversion factor, and then I always just like to write those units for the final answer. So I'm looking for grams of CO2. And so when I set up my conversion factor, I'm starting off with moles, so I need to put moles on the bottom here, moles of carbon dioxide. I'm trying to get into grams of carbon dioxide, so I'm going to put that on the top. Again, notice we have grams and moles, so that tells us that we need to find the molar mass, and that value changes for each substance. So this time we're working with carbon dioxide, so let's find the molar mass of carbon dioxide. So carbon, there's one carbon, and it has a mass of 12. Then we have oxygen. We have 2 oxygens, and it has a mass of 16, so that's going to be 32. So our mass here is, molar mass is going to be 44 grams. So I'm going to put that value here, 44 grams for 1 mole. So we just go ahead and do the math on this. So this time we're just simply going to take 88 times 44, and we could divide it by 1, but we obviously don't need to do that. And so let's see what our value is going to be. This time we calculate that our value is 3872. Notice though that there's 4 significant figures there, and we only want 2 significant figures in our answer. So what we're going to have to do is we're going to have to go 1, 2, look at the third one is bigger. So our real answer here is going to be 3900 grams of carbon dioxide. And we put a box around our answer and we're done. So on this slide, we're going to talk about volume conversions. Just go ahead and read along with me. It says many of the chemicals we deal with are in the physical state gases. They are difficult to weigh, or to get the mass of, but we still need to know how many moles of the gas we have. So even though they're difficult to weigh, we still need to know how many moles there are. 2 things that affect the volume of a gas is temperature and pressure. So, how hot or how cool, and then how much space, like how confined are they. And then we need to compare all the gases at the same temperature and pressure because these 2 things can affect them. So that's why we have this thing called STP, which you'll see in a lot of our conversion factors, and that stands for standard temperature and pressure. And so the standard temperature that we measure at is 0 degrees for gases, and our standard pressure is 1 atmosphere. So at STP, 1 mole of any gas occupies a volume of 22.4 liters. And this goes for all gases. So if I have a 1 mole of any gas, doesn't matter what it is, it's going to take up a volume of 22.4 liters. And so this is called the molar volume. So this leads us to our 4th equality that we're going to use to solve these conversion factors, that any mole of gas at STP has a volume of 22.4 liters. So here on this slide, we're just going to see some conversion factors that we're going to do. And so the first question here, it says, what is the volume of 4.59 moles of carbon dioxide gas at STP? And we see the answer here, but let's go ahead and see how we set this up. So again, I want to box what I'm looking for. So I'm looking for volume in my final answer, and my given is 4.59 moles of carbon dioxide. So I'm going to set that up with my given, so 4.59 moles carbon dioxide. Then I need to set up a conversion factor, and I'm trying to get into liters. Well, on the last slide, we found that our conversion factor was that for every 22.4 liters, that's equal to the volume of 1 mole, and I need to put CO2 here, 1 mole of CO2. So we're just going to do the math on this, and so 4.59 moles of carbon dioxide times 22.4 liters of carbon dioxide divided by this. Our units here cancel out, leaving us in liters of carbon dioxide, gives us a value of 103 liters carbon dioxide. You can set this next problem up very similarly. Again, we're asking for moles, and they're giving us liters this time, so we're starting with liters, so 5.67 liters of oxygen. My conversion factors this time is going to need to have liters on the bottom of oxygen, and then since I'm trying to get into moles, moles will need to be on the top. Again, I know this conversion factor is 1 and 22.4. And we just do the math on this, where I take 5.67 liters, divide it by 22.4, and this is our value, and we should include the element that we're dealing with. So our final answer is going to be 0.253 moles of oxygen. Now our last problem here is pretty tricky because we want to look for volume, but notice they're starting us off in grams. Well, I don't know, so sorry about that. As I was saying, they're asking us to find volume, but they're giving us grams, and we don't have a conversion factor that gets us straight from grams to volume. So we're going to go ahead and need to use two conversion factors for this. So let me go ahead and show you how I'll set up this problem. So I always want to go ahead and start with my given. I already said that I knew that I was going to need two conversion factors, and this is what I'm looking for. So a couple of things that I know where I need to put my conversion factors already is, well, I know my final answer is not going to be in grams, so I'm going to need to cancel out my grams here. And I know that I'm going to need to get into liters over here. So that needs to be in the top half of the last conversion factor. So do I know anything with grams? Yeah, I can do a little molar mass. So for every 1 mole, the molar mass of methane here is 16. And I figured that out because carbon has 12, then there's 4 hydrogens, so that makes 16. And then over here in our second conversion factor, we have 22.4 liters. That was the conversion factor we just got from the last slide, is equal to 1 mole. And I should write methane right here. And so the important thing to notice is this grams will cancel out here, this mole will cancel out here, and our final answer, which we're looking for, is going to be liters of methane. So the way that we do this math is we're going to go 8.8 times 1 times 22.4, then divided by 16 and divided by 1. So when we do the math on that, that equals out to our value of 12.3 liters. So here are the conversion factors that you should have under your belt. Is this idea that 1 mole is equal to the molar mass of anything. 1 mole is also equal to 6.02 times 10 to the 23rd representative particles. 1 mole is also equal to 22.4 liters of gas at STP, and thus we can make these conversion factors from these 4 values. So really this is just the same as saying 12 inches and 1 foot. Okay, 2.54 centimeters in 1 inch. You know, like going back and forth. So just think of these as easy conversion factors, and you definitely should be writing them on your periodic table. So this section is really important because when we start getting into stoichiometry in the next chapter, you're going to need to be able to comfortably use all of these conversion factors.